Okay, good. So this is the, let me, so this is the title, this is the subject I will be talking about to you. And I will be mainly following the reference textbook, which is the Introduction to Physical Oceanography, and which you can find on net. It's published online. You can take it, and but nevertheless, I would you have obtained the program, the curriculum of this course, where there are a number of textbooks which you can use also if you want to widen your knowledge. This is the basic textbook, but anyhow, I will be using also other sources to present my lectures. What are the topics I will be talking about? In this introduction, this is the historical and physical settings, atmospheric influences, oceanic heat budget and water budgets. I must say that this part of the physical oceanography, physics of the sea, what I will be talking about is qualitative, descriptive. So this is a descriptive oceanography, and then you will have the chance to follow to follow more closely the part which is also presented by mathematical formulations and numerical solutions. Then I will be talking about temperature, salinity, and density, which are the most important parameters in the ocean. Well, I will be talking about the spatial distribution over the world ocean of all these parameters, which are then you will see how they are determining the flow, the currents. And then obviously we pass to the equations of motions, which are to a certain extent or largely related to temperature, salinity, and density, spatial and temporal distribution. So we have the equations of motion with and without friction. We have the response to the wind. We have geostrophic currents and wind-driven circulation. So by wind-driven circulation, I mainly think of the basin-wide, ocean-wide wind-driven circulation. Then I will be talking about the vorticity in the ocean, which is which is one important concept which is used to description of the current field. Then I will be mentioning deep circulation. It's very little about ocean waves, which will be talked later on in the next part of the course. Then I'll be talking about coastal processes and tides, and I will be a little bit presenting these problems on the coastal processes and tides in Venice Lagoon example, which is one of the classical example of how to deal and how to address the coastal processes and how these coastal processes are influenced by, for example, climate change and this kind of stuff. And finally, I will be talking about the observations, about the techniques, what we use to observe the currents, to observe and to measure temperature, salinity, and density, and all the other parameters. We'll be talking about the Eulerian measurements, where you do the measurements at a fixed point. And we will be talking about the Lagrangian observations, where you do your measurements by following the currents. And then we'll be talking about the remote sensing and in situ observations. Remote sensing means that your instrument is not immersed into the sea, but your instrument is above sea, outside of the sea, so it's on the satellite or on the land. And then we'll be talking about the in situ observation. So these are the topics what will be addressed during this course. And so this is something like a course syllabus. But you obtain the adjourned course syllabus which we sent you before the beginning of the course. So let's start. There are a number of questions, number of things what we put when we want to understand the physics of the oceans. First thing is, what are the physical properties of seawater? The physical properties of seawater are those which are related to the physical state of the ocean, of the seawater. So these are temperature, salinity, density. Then what are the important thermodynamic and dynamic processes influencing the ocean? Here will be, as the same time, we'll be discussing what are those processes which are important, and we will be setting up the kind of hierarchy of these processes in terms of their influence of the ocean. And also on the approximation what we use in order to simplify the thermodynamics and dynamics processes which are influencing the ocean, in order to understand it better, in order not to use everything, but to use these specific approximations. Then what equations describe these processes and how they were derived. So this is that's really comes later after this question B. What approximations were used in these derivations, because we will see later then the equations they don't contain everything, so they don't contain all the information. So we have to use the different approximations in order to obtain the simple solutions. Do the equations have useful solutions? Yes. The answer is yes or not. They do have useful solutions. I'm talking about analytical solutions in the case if we can linearize these equations, or we can obtain the solutions if we do the numerical integrations. Another important question is how well these solutions describe the process. Because since we obtained, if we obtain the solutions by doing the approximations, we do have to know what these approximations, what we have neglected by doing these approximations, and then obviously associated with this is what is the experimental basis for the theories where we obtain these simplified solutions. Then, obviously, as in every science, there are processes which are poorly understood, and these are which are well understood. So we'll be also trying to separate these relatively poorly or relatively well understood processes. And in order to deal with these questions, which we mentioned on the point one, we should see what are the sources of information about physical variables, because we have to know the limits of these sources, the limits of these instruments. And so when we use sources of information, we have to know what are the accuracy and limitations of these measurements. So the question is what instruments we use for measuring each variable. Why do we have to know this? Because we have to know what are the spatial and temporal resolution of these measurements, whether they measure every hour, whether they measure every day, or whether they measure every minutes, or whether they do their measurements every meter or every kilometer and so forth. So we have to know the resolution, spatial and temporal resolution of these instruments, apart from their accuracy and the precision. What the historical data exists, because you don't start when you approach or start to do the certain problem. You don't start from zero, from the scratch, because you have to know what historical data exists. This is one thing. The other thing is what are the previous knowledge of this of the process you are going to study. So you have to know both the availability of the historical data, again, understanding what instruments were used for measuring these variables, because also the instruments are changing with time. There is a more modern instruments to be used for measurements, and this is one thing. And then what is the precision, again, precision and accuracy of these historical data? What platform are used? Satellites, ships, drifters, moorings, because on the basis of and by knowing the platforms, we know we can have additional information on certainly a satellite measurements and does not have the same precision as measuring in situ from ships. Satellites, for example, do the measurements only at the surface, very thin surface layer. Ships, you can go deep into the ocean. Drifters, it measures the, again, very surface layer. Moorings, which are the fixed instrumentation in the ocean, they can measure all over the water column. So these information are essential when you are going to use these data. And then the third thing is what processes are important. Some important processes we will study include, these are heat storage and transport in the ocean. This is that's important thing. We will be analyzing the heat equation. We'll be mentioning and talking about the exchange of heat with the atmosphere and the role of the ocean in the climate. Only last 50 years or something, the role of the ocean in ocean climate has been appreciated much more. And so this is something what has to be addressed in a very careful way. Then the third process, or the third forcing, is wind, which is a mechanical forcing. So this which acts on the sea surface via friction, and thermal forcing of the surface mixed layer. Because the thermal forcing, what thermal forcing does? Thermal forcing can cool the surface layer, and by cooling the surface layer, can cause the vertical mixing of the water in the surface layer. While the wind does essentially the similar thing, but doing the mechanical mixing. And then we have the wind-driven circulation, including the Ekman circulation, Ekman pumping of the deeper circulation and upwelling. These are the subjects we will be addressing during this course. Now I jump over this thing, just giving you an idea that the early oceanographic measurements started in 17th century. And you can see here, for example, that there are also already starts with the trade winds, monsoons. That means the wind forcing and so forth. So the first studies which are related to the ocean starts is with the studies of the wind, and obviously, and then it went down to the ocean. You can see, for example, that already in the early 19th century, there was the meridional circulation of the ocean sinking, or the ocean with water sinking near the poles and rising near the equator. So this is 200 years ago. We already have some hints on the processes which are known on the on the ocean-wide circulation. You can see that at the end of the 19th century, first direct measurements of the Florida current, the most important and the strongest current in the world, has been done in the front of the Florida coast. This is the Florida current, makes part of the Gulf Stream current. And so you can see that the first measure started where the signal in the ocean is the strongest. The Gulf Stream is the strongest current in the ocean. The wind is something what we feel. So these measurements started earlier, because that's also a lot of tidal measurements has started very early. In the late 18th century, Laplace published his theory of tides, because this is something what also staying, you don't even have to go to the ocean, stay at the coast and see the tides, how they are doing, and so forth. This is a famous William Bjerknes dynamic meteorology and hydrography. The first, the Woods Hole famous Oceanographic Institute has been founded in 1930, and so forth. First oceanographic satellite has been launched in 1978. So before that, there was meteorological satellite, and this in 78 is the remote sensing satellite of the oceanographic data, so this is the and so forth. Just to give you an idea, here is the in 1990s the drifters that continuously measures current at depth of 2 kilometers. So you have the vertical profiling of the current up to 2 kilometers in the ocean, which are following the current. First satellite measurement of the sea level started in 1992. So this is another historical data in the development of oceanography. Yes, 1992 is the launching of the satellite Topex Poseidon, which maps ocean surface current, waves, and tides every 10 days. And so where we can, which helps us to understand ocean dynamics and tides. You will see later on how we can learn from the sea level the ocean dynamics. That means the forces which are acting on the surface currents, and how we can obtain the flow from the surface pattern. So these are the evolution of some theoretical ideas. For example, theory of turbulence is in 1940, 1970. Analytical hydrodynamics and land hydrodynamics is 19th century. Bjerknes develops geostrophic methods widely used in meteorology and oceanography. This is the 19th century. In 80s, there's a mechanics of chaotic processes. So these are the evolution of some theoretical ideas. What about the C2 measurement, the measurements from the ships, the measurements, or in general oceanographic measurements in the ocean, which started in late 19th century. And here you can see this is the famous Challenger cruise, which has been done in 5 years. In 5 years over the entire world ocean. You can see what what is the ship tracks of this Challenger ship, and this, for these measurements, it took 4 or 5 years. So can you imagine? Interpreting these data means that you have somehow to forget about the time lapse between the different points, between this point here and that point here, even though it passes like 3-4 years. So you have to assume the synopticity. So the measurements at the same moment over the entire ocean. This is something. This is the assumption which is pretty valid if we are talking about the slow processes. If we are talking about long-term changes about the climate scale distribution, but obviously this is much more disturbed by the short time scale processes. Therefore, when you're interpreting these data along these tracks, you have to be very careful in what you see, and be careful not to mismatch the short-term signal with the long-term signal. And obviously, with using the much modern ships and modern instruments, the coverage was much better, much finer in the space, but also shorter in time. For example, all this coverage, which is is clear, is oriented into the southern Atlantic, is covered in 1 year, in 2 years, sorry. It's covered in 2 years, and all these points, these are the points where ships stopped and did the vertical measurements from the surface to the bottom. So this is in 2 years. What that means? That means that the instruments were much more modern. They respond to the signal in the ocean, so you can do these measurements rather fast. And so this is that's a national systematic survey which has been done by German RV Meteor ship. The era of the new methods, which is, for example, the Atlantis cruise out of Woods Hole. The Woods Hole Institute is here, and you remember the Woods Hole was founded in 1930, and all these measurements has been done by Woods Hole. Obviously, they were interested in, for obvious reasons, they were interested in the northeastern Atlantic, in this part here. Why in this part here? First of all, they are here, they are situated here, is Woods Hole Institute. But not only that, here is the area where there is one of the strongest flow in the world ocean, which is the Gulf Stream, Florida, and the Gulf Stream, which flows this way, northeastward. Therefore, these measurements were extremely important in describing how this Gulf Stream looks like and what are the specific features of the Gulf Stream. Then we have international cooperation. International cooperation means that the number of nations all over the world has been included, and this is the famous International Geophysical Year Atlantic Program, which has been realized in 1957-59. And these transects consist of has been done by a number of ships of different countries, and this you can see how the distribution of stations and distribution of transects has been used to give a very detailed description of the flow of the horizontal and the vertical distribution of water masses, vertical distribution of temperature and salinity. So you will see how we will be using the salinity, for example, as tracing the water masses, as tracing where these water masses are expanding or distributing. This is another very great international worldwide experiment, which is World Ocean Circulation Experiment. And this is the tracks of research ships making a one-time global survey of the ocean on Earth. That means they passed over the entire ocean within 2-3 years. And this is the World Ocean Circulation Experiment, famous VOCE. All these, after all these great international or even national coordinated experiments, the oceanography had a great impulse in understanding what is happening in the world ocean and how the circulation is driven, what is the distribution of the water properties of the parameter state of the world ocean. And finally, here we have example from the era of satellites. This is a topics Poseidon, which started in 1992. These are tracks of in the Pacific Ocean during a 10-day repeat of the orbit. So this pattern, this distribution of the measurements, all these lines are measurements along which the sea level has been measured, sea level and tides, obviously. And this is in 10 days. This coverage has been done. So every 10 days you get these coverage. So can you imagine what wealth of data we obtain from this kind of measurements? As I mentioned before, this is the top 5 famous topics Poseidon project. The satellite, the system of satellites is still active, and we obtain on a regular basis the data since 1992. So that means so far we have like almost 30 years of data, which then helps us to understand what is the long-term changes of the sea level. Because before what we have had at our disposal are the sea level measurements along the coast on the tide gauge instruments, which has been put, you have a certainly limited number of tide gauges, the instruments which are measuring sea level. And after that, in the satellite era, these are the information we obtain. So we obtain not only information along the coast, but we obtain the information in the open ocean. So this wealth of data helped us to first of all to understand what is the basin-wide behavior of the sea level, and then you will see how the behavior of the currents. But not only that, we would obtain the long-term changes on a 30-year time scale, not enough long to understand the long-term climatic variations, but on these 30 years, 3 decades, we see how the sea level, the mean sea level of the ocean is changing. And this is very important information when we are talking about the climate change studies, and we will be talking about this much more later. So, and yeah, coming back to satellite measurements, the information what we obtain from satellites is related only to the surface. So this is the problem with the satellite data, because they reach only the surface. You don't know what is happening below. In order to get the information in the water column, you have to do the measurements in the vertical. And so you cannot do only satellite measurement. You always have to do what we call in situ measurements with ships, with the moorings, with drifters or floats, in order to obtain the information below the oceanographic information below the sea surface. And now we have to design. We should design, if you want to study one process, or we want to study theory or whatever in the ocean, we have to design our experiment. So what kind of stuff we have to think about when we design our experiment? The first and most important aspect of the design of any experiment is to determine why do you want to make a measurements before deciding how we will make those measurements and what we measure. So we have to understand what are the purpose of our measurements. Do we wish to test the hypotheses or describe processes? This is one thing. What accuracy is required by the observation? For example, let's talk about a very simple example: the tides. Okay, if you know that the tides in, for example, along the coast of England, the tides have amplitudes on the order of a meter. We don't need there the accuracy of 1 millimeter. It's enough to have the accuracy of a centimeter or even a decimeter, right? If we want to, if we have, as far as temperature is concerned, for example, in the ocean, we know that the temperature in the ocean changes, in the open ocean changes on the order of 1/10 of a degree. So we cannot measure the temperature with accuracy of 1 degree if you want to have the resolution of 1/10 of a degree. We have to have the resolution which is at least 1/100th of a degree. Then the third thing is what resolution in time and space is required, and what is the duration of measurement. These two questions have to do with the time scale, what we want to study, or with the time scale of the variations of our process we want to study. The resolution in time and space is required, is determined on the basis of the time and space scale of our process, of the processes we want to study. Again, if you go to this very simple example of tides, then we know that tides are changing on a time scale of on the order of half a day. Okay, so in order to study the tides with a satisfactory time and resolution, you have to have the resolution. You should have the resolution on the order of half an hour, not more than that. Obviously, considering that you might have the variabilities in the sea level which are shorter, on a shorter time scale than the tides, in that case, you have to somehow to take into consideration the shorter processes. Space scale again depends on the space of the process we are talking about. We know that, for example, to give you an example, the Gulf Stream, which is this famous current in the ocean, has the width. The width of the Gulf Stream is on the order of 100 kilometers. So if you want to study the Gulf Stream with a satisfactory space resolution, then you have to cross the Gulf Stream with a ship where you have the resolution on the order of a few kilometers in order to get the fine scale structure of the Gulf Stream. The duration of the experiment is determined again on the time scale on the processes. If we are talking about, again, going back to tidal example, we cannot do our measurements cannot take we cannot take the measurements of tides to describe tides, which if you have the measurements of half a day, you have to have the multiple of a day in order to get the good description. The longer is your duration. The more data, the more days you do your measurements, the better is the description of the tides in a given space. So you cannot. Here is some closed circle. In order to study a certain process, you have to know something about. You cannot start studying a process without knowing absolutely anything about the process. You have to know something, and then on the basis of your knowledge, of your previous knowledge, you decide what accuracy, what resolution, what space in space and time, and what the duration of the measurements. So only in that way you can determine in the right way your measurement strategy. Here is something what I already mentioned before, but now let's specify, let's define more accurately or precisely. Accuracy is the difference between the measured value and the true value. Okay, so this is the accuracy. And the precision is the difference among repeated measurements. So in order to get the precision of an instrument, you have to do the number of repeated measurements in the same conditions, and then you obtain the precision. While the accuracy is the difference between the measured value and the true value. Okay. So now let's go to physical settings. Let's try to give some description of the ocean. We have to give some description of the ocean, the bottom, the horizontal and vertical extension, and so forth. Because this will help you to understand the processes, or to describe the processes, or to see what you could expect in a certain part of the ocean. For example, this is one thing. What is important is the histogram of elevation depth of the seafloor. This is the depth. This is the distribution of the depth of the ocean, and you can see that the ocean depth changes from 0, obviously, to 6 kilometers, with the maximum concentration or maximum frequency of depth around 5 kilometers. So the major part of the ocean is like a 5,000 meter deep. And this is something what you usually when you think of the ocean, you think it's not so deep, but major part of the ocean is a 5 kilometer deep, 5,000 meter deep, and and this is almost a normal kind of distribution of depth in the world ocean, which is not the same thing as the height of the land, height elevation of the land above the sea level, which is most part of the height is around 0, and then you have here the going to higher heights, the smaller is the frequency of the heights. Here is a cumulative frequency curve, which is essentially gives the same information as this one. Now this let's see what are the pattern of the features of the seafloor. The pattern or the features of the seafloor have specific features which has a specific name, so that and have a specific physical and geological characteristics. By having a physical characteristics, automatically it gives you the idea of what are the characteristics of the ocean in this part of in this features of the ocean depth. This is that's the cross section of an ocean. Consider that we exaggerate the vertical scale with respect to the horizontal scale, because here is, as we said before, is around 4 or 5,000 meters, 4 or 5 kilometers. And in the ocean, typically ocean is large, like 5 to 10,000 kilometers. So so we have squeezed the horizontal scale and or stretched the vertical scale in order to see something. So what we see is there are continents on the border of the ocean. We have a shelf. The shelf area has this defined as an average slope. 1/500 is the slope. It's a relatively low slope. And the shelf is defined as coming up to 200 meters depth. After the shelf, there's a slope area which has a much steeper slope, and this is on one hand limited by the shelf, on the other hand by the basin. And then there is the center of the basin, which is, as I told you before, mainly of a 5,000 meter deep. In the middle of the ocean, typically, this is the zonal cross-section of the ocean. In the middle of the ocean, we have a mid-ocean ridge, which goes north-south, more or less north-south direction. And then you have also a number of seamounts like a mountain, like a relatively small mountains in the ocean. Then you have a trench, which are limited area, which are very deep, which goes in the ocean. You probably have heard around 11,000 meters. Then you have islands, and then finally you get again the continent. So these are the main features of the ocean. They are characterized by the type of sediments, obviously, because there are different current velocities, and so they determine the different sediments. The slower the velocity, the more fine are sediments. Okay, so here are the description of these things. The basin is a deep depression of the seafloor. Canyons are relatively narrow, deep furrows with steep lows cutting across the continental shelf and slope, with bottom sloping continuously downward. These are the remnants of the rivers, of the river beds which were entering into the sea. Then you have a continental shelves, as I told you before. These are adjacent to continent. Continental slopes, we already seen this. These are the acclivities seaward. Plains are very flat surfaces found in many deep ocean basins. Then we have ridges, seamounts, sills, and trenches. So these are the description of what I already showed to you let's cross about this. This is the cross section of the South Atlantic along the 25 south. This is how it looks like in a real ocean. You can see that more or less what we have seen before in schematized feature of the ocean bottom. Here is shown very clearly in the real ocean, in Atlantic Ocean. You can see here the slope. You can see the seamount. You see these. This is the ridge, and here is again the slope and shelf. What is important with these two, if you compare these two figures, this upper figure is exaggeration of 180 versus 1. So we exaggerated the vertical scale with respect to the horizontal scale. If we do this exaggeration only 30 towards 1, which is the lower figure, you can see that the features we don't see at all. So this is why we do this exaggeration, in order to present what is happening in a real ocean in the vertical. Otherwise, if we shown the true aspect ratio, the ratio between the horizontal and vertical scale, the plot would be the line practically. So the line would be, and we wouldn't see anything. And this is something what we don't want. We want really to see what is happening in the ocean in the vertical scale. In order to do that, we exaggerate the vertical scale with respect to the horizontal scale in order to see this. So remember, all the time from now on, we will be considering this kind of graphs where we are exaggerating like 180 times the vertical scale with respect to the horizontal scale. World ocean bathymetry. World ocean bathymetry is can be seen from let me see. Can be seen from the sea level. How it can be seen from the sea level, measured from the satellite. Let's go back to here. Here is this is the seafloor. Okay, the seafloor, and you can see that the sea level corresponding to the sea surface of an ocean at rest is a special surface which is geoid. This one is geoid. To a first approximation, a geoid is an ellipsoid that corresponds to the surface of a rotating homogeneous fluid in a solid body rotation. Solid body rotation means that the ocean rotates with the same velocity as the Earth, which means that the fluid has no internal flow. So, if the ocean does not have an internal flow, and if the ocean rotates together with the Earth, solid Earth, in that case, the sea surface will have the form of ellipsoid. But since the geoid, which is called geoid differs from the ellipsoid because of local variations of gravity. Why? Because if you have the seafloor, and the seafloor is deformed in this way, so you have here a seamount, for example. What is happening? You have here more mass on the seafloor than here, and the geoid, which is defined at the surface, as the surface where the sea surface where the gravitational force is perpendicular to the sea surface. Here we will have more mass at the bottom than here. So in order to get the sea surface being parallel, being a geoid, and the sea surface has to have perpendicular gravitational force to it, and therefore the sea surface will be deformed due to the deformation of the bottom of the ocean bottom. Therefore, what that means? That means that we can, looking at the sea surface, we can understand what is the bottom shape. So by doing the satellite sea surface measurement, this is another important information what we can obtain is the bottom shape, the bottom pattern. In fact, here you see in the figure description, the seamounts are more dense than seawater. Therefore, the increase of local gravity causing a plumb line of the sea surface, this is the plumb line, the gravity direction, to be deflected toward the seamount, you see. And therefore, in order to do that, because the surface of an ocean at rest must be perpendicular to the gravity, as we have defined it before, the sea surface and local geoid must have a slight bulge, as shown here. Therefore, bulges or the deformation in deeper are corresponding to seamounts or the deeper part of the ocean. So what you can see here, for example, this reddish part here or yellowish part here, these are the ocean ridges. You can see that ocean ridge in the Atlantic goes from the North Pole to the South Pole. A similar thing is in the Pacific, not completely, but the same thing or similar thing you can see in the Indian Ocean. So what we have taught before, the ridges are really present. Then you have a number of sea mounts in the ocean. The reddish, very red colors represents very shallow water, so you can see all around the world ocean with a different width the shelf areas. And here is, for example, if you zoom this to the Atlantic Ocean, you can see again the large shelf along the eastern coast of the United States, relatively narrow shelf along the Africa and Europe, and then here a clear mid-Atlantic ridge and some number of sea mounts here. Here is an example of continental shelf in front of the California coast. And these are the canyons here. You can see that these canyons are very similar to the riverbed, and they are really a continuation of the rivers which are coming into the sea. This thing here, this relatively flat area, is the shelf, and then there are a number of canyons which are crossing this shelf area. Okay, so that's a kind of a simple introduction which we will be using later on for our consideration, for description of various basins, for understanding why currents are here like this and in the other ocean different. So all these, what we have done so far, this pattern, are certainly influencing the ocean currents and dynamics of the ocean. So now let's talk about the oceanic heat budget. Oceanic heat budget means that what is the really difference between the input heat and output heat. This, in theory, has to be zero, and it is zero and almost zero in the first approximation if you consider the entire Earth. If you do the integral over the entire Earth, then obviously this should be zero, because we don't have the at least important heating. Not talking about the climate change, but we don't have important heating of the Earth. Therefore, if you do the integral over the entire world ocean, then we will have the heat budget zero. However, if we do the different parts of if we consider different parts of the ocean, this certainly will not be zero. There is and there will be, there is the parts of the ocean when the heat loss is larger than heat gain, or vice versa. Anyhow, the sum of heat fluxes into or out of a volume of water is the heat budget. This is the definition of the heat budget. So the major terms in the budget of at the sea surface is insolation, or the energy comes from the sun. We have the net infrared radiation, the net flux of infrared radiation from the sea, which is proportional to the temperature, to the sea temperature. Sensible heat flux is the flux out of the sea due to the conduction. So simply contact between the atmosphere and the ocean determines the sensible heat flux, or the difference between the temperature between atmosphere and the ocean. Then we have the latent heat flux. The latent heat flux is the flux of heat carried by evaporated water, because the water evaporation contributes to the loss of heat from the sea surface. And finally, we have advection, heat carried away by currents. The first four components of the heat budgets are sources or losses of the heat. Advection is simply a redistribution of the flow within the ocean. This is a very important. This is a very important component because of what I said before. The Earth in general, if you do the integral of the heat budget over the Earth, this is zero. However, between different parts of the ocean, there is a heat loss or heat gain in function of whether ice insulation is stronger or high or low, weaker than infrared radiation sensitive heat, latent heat, some of these 2, 3, and 4, or is insulation is stronger than these 2, 3, and 4. To help in this redistribution of the heat, the advection of heat takes care, because the redistribution of heat tries, or currents are trying to smooth down the differences in heat between the area where the heat loss is larger than the heat gain, or vice versa, and vice versa. The same thing is happening exactly the same thing is happening in the atmosphere. In the atmosphere, again, the flow, the airflow, or the winds are taking care of redistribution of heat. Okay, here is this dashed line is the black body radiation at the 5,900 Kelvin, which is the temperature of the sun, and this is the this is the solar radiation above the atmosphere. So you can see how these two curves goes very well. So the radiation of the solar radiation is before it comes into the ocean is very well approximated by the black body radiation at the temperature of the sun. Solar radiation at the surface obviously has been reduced. Not everywhere the same reduction of the solar radiation in function of wavelength. Why is it reduced? It's reduced because the atmosphere absorbs the radiation which comes from the sun. So these differences between these two is due to the absorption of the heat due to the atmosphere. Here is the number of variables and units and so forth. I won't go into this detail because it's too complicated. And here is the mean annual radiation and heat balance of the Earth. It seems very, very complicated, but with a little bit of patience so we can understand this. Here is the incoming solar radiation, which is this integral below this dashed curve, and this comes reaches the atmosphere. Part of this solar radiation is absorbed by the atmosphere. The rest comes to the surface, to the sea surface, or to the land. Part is reflected back into the space. Part of the solar radiation is also reflected by clouds, aerosols, and atmosphere, and goes back into the space. Then the sun is heating up the surface of the Earth, and so this surface radiations goes back into the space. The surface radiation is again black body radiation proportional to the temperature of the Earth's surface or the ocean surface, and then it goes partly is absorbed by greenhouse gases. You can see that there are greenhouse gases which has been always present in the Earth not only now when we are increasing the number of the concentration of greenhouse gases. They are always present there. If greenhouse gases were not present in the ocean, in the atmosphere, the Earth would be like a 20 degrees or colder in average than it is now. So we have now the temperature, the atmosphere temperature around 15 degrees. Without greenhouse gases, it would be like -5 or something like that. It wouldn't be appropriate for the life, human, for the living organism. Then there is the outgoing long wave radiation, which goes into the space. Greenhouse gases. This component is important. The greenhouse gases are absorbing partly this surface radiation, and they are back radiating this energy into the atmosphere, keeping the atmosphere warmer than it would be without greenhouse gases. Then we have evapotranspiration, and then we have a thermals or latent heat. So this is the relatively complicated, but on the other hand, not very complicated scheme of the exchange of heat between the atmosphere, between the Earth and the atmosphere. Here is the heat flux component as a function of meridional as a function of north-south. Here is the minus the 90, plus 90. This is the equator. This is the southern pole, south pole, north pole, and this is the solar radiation. This is the long wave radiation. No, sorry. This is the insolation. That's insolation, which reaches the ocean. This is this thing here, and you can see that it has a maximum around the equator, which is small minimum, local minimum around the equator, which is due to the almost to very strong cloudiness in that area, to strong cloudiness in that area, and therefore the solar radiation which reaches the Earth is slightly smaller than on both sides of the equator. Then if you go toward north or toward south, the solar radiation diminishes, and because the sun is lower in the horizon, the more you go toward the poles. Then we have the sensible heat flux, is the smallest component. Latent heat flux is this one here. Latent heat flux is again shows a minimum around the equator, and then we have a long wave radiation, which is due simply to the temperature of the Earth or of the ocean. And here, if you do the sum of the two, the sum of all these components, we have a total heat flux. You can see these continuous line. Okay, and this continuous line shows that there is this there's more heat reaching the ocean in the equator. Then there is a loss of heat in the polar areas. How this can be compensated? This is compensated by the wind or currents flowing from the equator, bringing from the equator to poles the warmer water. So already here, this this thing gives you the idea that how in the first approximation the current should flow. The current should flow in such a way that in the surface they will carry the heat from the equator to the poles. So that's and the same thing happens with the wind. Okay. Here is the annual mean heat flux. This is what we have seen before. This is the integral over the entire Earth, and here is how it looks like in a horizontal distribution over the entire ocean. So this is the mean heat flux through the sea surface, calculated from numerical modeling data reanalysis, and bluish lines, they give the heat loss. Sorry, the heat gain, and the reddish lines, reddish. It's usually, you know, when C1 blue means the loss, but it's not the case. And here you can see the reddish color is the gain, is the loss. Why? So what we can see here, that in the first approximation, yes, the gain or loss is distributed in a zonal direction. Obviously, that's not always true. For example, this heat loss at the sea surface here along the coast of North America, or around the coast of North America, or along the coast of Asia, northeastern coast of Asia, is something which is departs from the zonal distribution, because on the other side you have the heat gain. Why is this so? This is determined. This is due to the current flow. So the departures from the zonal distribution of the heat loss or heat gains is due to the currents. For example, the same thing as you can see here, you can see at the southern hemisphere, exactly at the same area, you can see this reddish color here and here, and along the Australian coast. Well, you will see later on when we are going to talk about currents, you will see why this is so. But I can reveal you the secret, and these are the western current, western strong currents in all the oceans, which are bringing the warm water from the equator toward the North Poles, toward the poles. Gulf Stream, Kuroshio, Eastern Australian currents, and so forth. So they are creating those departures. On the other side, you can see this asymmetry between the eastern and the western coast. What that means? That means that here you have the flow of the warmer water toward north, and on the other side, on the eastern coast of oceans, you can see the colder water. So that means the cold water is flowing from poles toward the south. Or in this case is something else, which I have to correct myself and have to give you the wrong idea. This is something what we call upwelling. So that is the upward motion of the deeper waters into the surface, which are then creating this discrepancy or the asymmetry between east and western part of the ocean. And this part here, this asymmetry here, is created by the wind. This reddish part is created by the differences in the temperature between the poles and equator, in differences in the heat content. Okay, so here is the transport. Okay, the transport should somehow take care of this asymmetry on these differences between the polar and equatorial areas. So if you do the northward transport over over the entire world, in the entire world ocean, what you get is this curve here. Total transport, this is the total transport of heat. Here is the transport toward the south. Here is the transport toward north. You can see the maximum is around 20 degrees of the heat transport. The Atlantic Ocean is a dashed dot line. And Atlantic Ocean gives you the mainly southward transport. The northward transport is relatively weak. We will see later on why is this so. And then you can see the Indian Ocean. The Indian Ocean has only the southward, toward the south, to the South Pole. You have the heat transport, because the Indian Ocean doesn't have a northern part. So only the Pacific and Atlantic, they have both. They extend both to the north and south, even while the Indian Ocean has only its northern part. So this is that's to give you an idea how it looks like. Obviously, at the equator, the transport or heat transport is zero. This is the change in solar constant. I won't be talking about too much this, except that there are weakening of the solar constant, of the solar activity, or the availability of the solar heat. And partly depends also on enhanced volcanic activities. So you can see this mostly volcanic forcing is, for example, appears in early in 19th century, which then determines the solar constant, the solar irradiance. And so it's not that the solar radiance is determined only by solar activity. It's determined also what is happening in the Earth atmosphere. This is that's the strong volcanic forcing. And if we have the solar plus man-made forcing, you can see that the solar constant or global sea surface temperature increases, because we have, on one hand, we have increase of solar activity, which is due after this intense volcanic forcing. But at the same time, we have a man-made forcing in the atmosphere, which then causes the sea surface temperature increase. This is that's the development of the sea surface temperature in the last 400 years. Let's go this way. Okay, so now we can go on and consider the parameter of the parameter of state of density. And just a minute, I just wanted to tell you, since you are all muted, if you have questions, maybe it would be good that you send me by mail all questions you have, not only considering this what I have told you, but all the questions regarding whatever you want, not personal questions. You just write down the mail, send me the mail, and I will try to answer you before the next lecture. So if you send me by tonight, if you send me your questions, or if the questions are not so difficult, I will try to answer you the day after tomorrow. Okay, maybe that's a good idea. Instead of otherwise we can. There is another possibility. But let's try this way. You don't have my mail? No. Okay, I will. At the end, I will write down the the apo and write down my name, my mail. Okay. So I will have maybe some time to talk about the temperature, and then I will write down my mail. So here we are talking about temperature. The physical processes in the ocean depends on temperature. The unit of temperature obviously is the Kelvin. But the measurements of temperature using an absolute scale is difficult, and it is made by National Standards Laboratory. The absolute temperature are used to define a practical temperature scale based on the temperature of a few fixed points and interpolating devices which are calibrated at the fixed point, because we use the devices to measure the temperature. And these devices are calibrated by absolute temperature in laboratory conditions, and then we interpolate for these number of fixed points, we interpolate between them in order to calibrate the instruments. We have two, what we define, two types of temperature. One temperature is in situ temperature. So that means the temperature what we measure in situ at the place that our instrument is located. Potential temperature is defined as the temperature of a parcel of water at the sea surface after it has been raised from some depth in the ocean adiabatically. So that means, what that means? That means that by raising this water parcel from a certain depth adiabatic to the surface, we really bring the parcel to the pressure zero. And since this process has been done adiabatically, the parcel will expand. By expanding, its temperature will be diminished. So we are measuring we are introducing the temperature, potential temperature, which is not influenced by the pressure. So all the temperature which measure at a larger depth has been corrected by the influence of the pressure. And we will see later why do we do that. Sorry. The measurements of temperature are done with instruments that have an accuracy of millidegree. This is what you remember when we were talking about. The temperature in the ocean changes on a tenth of a degree or hundredths of a degree. Therefore, the accuracy of our instrument should be of a millidegree, and that's the only way we can distinguish different areas with different temperatures. Otherwise, you wouldn't be able to distinguish different temperatures with different areas if we have 1 degree Celsius precision measurements. The accuracy. The accuracy of a millidegree is not obtained by satellites. Satellites typically have the accuracy on the order of between 1/10 of 1/100th of a degree, and this is to a certain extent justified by the fact that at the surface, the sea surface temperature changes to a larger extent between different parts of the ocean, because because you have influence of vertical mixing of the heating and so forth, and this brings the differences of temperature larger than it is usually in the deeper part of the ocean. In the deeper part of the ocean, millidegree accuracy serves very much. In a surface, there's such a high degree is not essential. But on the other hand, the satellite gives you the possibility to determine the horizontal distribution temperature over the larger area, not as if you do the in situ measurement. let's see. Here is the that's the temperature. That's the vertical distribution of temperature. This is the graph which shows the vertical distribution of temperature from 1,000 meters to 8,000 meters. Okay, so this is the that's the in situ temperature. In situ temperature is this one here. Okay, we denote it by T capital letter T. If we if you do the calculation of the density from this, to do the calculation of density, you have to have the temperature and salinity data, because these two variables determine the density. If you calculate the temperature, the density, this is the density distribution. Okay, let's forget for the moment the salinity. If you look at these this density, what you obtain is that at the deeper part of the ocean, starting somehow from 4,000 meters, the density starts to increase. Okay, but can we have in the ocean the decrease? Sorry, can we have in the ocean the density in deeper layer smaller than the density in the upper layer? No, because this is the unstable equilibrium. The equilibrium is unstable, and therefore, almost immediately, the water column mixes vertically in order to obtain or vertical homogeneity or the higher density in deeper layer than in the upper layer. Therefore, this is this artifact due to the influence of the pressure. Therefore, what we do, we eliminate the influence of the pressure introducing the potential temperature. This is the potential temperature theta. And you can see that the potential temperature theta is smaller than the in situ temperature. And here in a layer deeper than 4,000 meters, there is no more instability. There is no more lower density in deeper part of the ocean than in the higher part of the ocean. Therefore, we reached in this way the vertical stability of the water column over the entire water column from the surface, or from 1,000 meters to 8,000 meters. This problem of the potential density is not so important for upper 1,000 meters, but it becomes really important for a deeper part of the ocean. Just to give you an idea, you see that if you look at the temperatures of the ocean here, you can see that it goes to 0.5 degrees above zero. So this is you can see that the part of the ocean is very cold. The largest part of the ocean volume has a very cold water. Okay, this is an example. This measurement has been done in the Kermadec Trench in the Pacific. So you can see that the depths are over 8,000 meters. So and the average ocean depth is about around 5,000 meters. So this is the and so this is something what this is a very nice example. How do we use the potential temperature in order to avoid the pressure influence on the density of the seawater? Okay, so now I will stop here. I will write down for you my mail. I use this one. Just a minute. Okay. Okay, here is my mail. Can you copy it? Okay, please copy it, and, and any question you have or arrives to me by tonight, I will try to reply. But please don't make difficult questions. Okay. Okay, so I wish you a good day. Today is nice weather. You go for a walk, not far away from the home. So have a nice day, and see you the day after tomorrow. Bye.
Thank you.
Bye.
Thank you. Bye.
Bye. Bye.
Thank you. Bye.